Okay, today we're going to talk about something we actually talked about a few days ago, a week or so ago. I don't know. We're going to talk about the values of sine at each of these angles around our unit circle, the ones that we know, not every angle, but the ones that we know. Sine is the what, guys? Sine is the y, right? So what I'm going to do is I'm going to think about when I'm at this point right here, we should know that y is what value? 0. Okay. When I'm at pi over 6, though, I'm gonna use a line so that these look nicer. When I'm at pi over 6, the y value goes straight down. The y value goes straight down. Okay, and do you guys know what sine of pi over 6 is? 1/2, thanks. All right, and then sine of pi over 4 is 2 over 2. And the sine at pi over 3 is 3 over 2. And the sine at pi over 2 is 1. So we can see that our y value is increasing. And then it gets to pi over 2 and it's 1. But then at 2 pi over 3, what happens to the y value? Yeah, it starts going down and then down and then downer and then eventually at pi we go all the way back down to 0. But if you look at the very top edge of where each of these y values hit, look at that top edge. This I'm not going to be able to make look nice, but if I connected all of these, they would make a nice, beautiful, smooth curve. Oh. Yeah? Okay. Now, when we go into the third quadrant, our y values start to get longer again, except what also is different about the third quadrant? They're negative values. So we're going more negative and more negative until we get most negative at -1. And then we get less negative. Why that thing keeps popping up. We get less negative and then lesser negative and then less negative all the way back down to 0. And you can see that the bottom ones make a very nice, relaxing, that's not relaxing, relaxing curve. Nice, beautiful curve down there. So what we're going to do today, though, is we're going to take our input, which is going to be the angle, and our output, which is the sine. Our input is the angle, and our output is the sine. So if I were making a table of all of these values, which I'm totally not going to make a table of all of them, but if I were, it would start with 0, 0. Oops, I didn't mean to make that 0, 0. And then it would go to pi over 6, 1/2. Then we go to pi over 4, square root 2 over 2. Then we go to pi over 3, square root 3 over 2. Pi over 2, 1. 2 pi over 3, square root 3 over 2. I'm not going to keep writing all of these, okay? But this is what I'm doing. I'm making my inputs the thetas and my outputs the sine values. Okay? Then what we're going to do is we're going to plot those. And you know what? We're going to plot those on the other set of notes. We're going to plot those on the other set of notes. So I'm not going to waste my time and plot them right here. But that's what we're going to do next is we're going to take the x and the y value, and we're going to plot those as an x value being the angles and the y value being the sine of that angle. Go to the next page in this packet, and now we're going to look at the cosines. So for each of the angles, we're going to look at the cosines. And I'm going to do the same thing I did. We're going to talk about the cosine, but the cosine is which for each of these angles. Cosine is the length of the x. So for the first one, you can see that for 0, the length of x, I meant that to be a different color, to be blue. The length of x is the longest one, which is 1. And then at pi over 6, my length of x is square root 3 over 2. At pi over 4 is square root 2 over 2. Pi over 3 is 1 over 2. And then at pi over 2, it's 0. So you can see our x's starting at their maximum of 1 and getting less and less, or smaller and smaller and smaller. Then what happens when we go to the second quadrant for the x's? They go negative. So now I'm in the second quadrant, and we're going to look at the x being negative a half, and then negative square root 2 over 2, and then negative square root of 3 over 2, all the way until we hit negative 1, which is the longest it can possibly be negative. Into the third quadrant, it's less negative. And then less negative, and then less negative until we get to 0. And then in the fourth quadrant, it changes to positive again. It goes positive, more positive, all the way back to 1. Now, that's one time around the circle. There's nothing stopping me from going multiple times around. But why am I stopping from doing multiple times around right now? Why am I stopping from doing that? Because it repeats. It's going to be the same thing over and over and over again. Okay? Ooh, what's that word? Cyclic? Vocab. Nobody knows. There's a cycle. It repeats over and over again. There's a word. Cyclical? Is that the right word? Yeah. This didn't sound right. But yeah, it goes over and over again, like it repeats over and over again. Okay, so let me draw the beautiful curve like I did for sine. I'm going to do the same thing for cosine. So there's this beautiful curve. It's a beautiful curve. I only colored them different because some of them are negative and some of them are positive. Now this is a teeny bit, ooh, I know what to do. I was gonna say this is gonna be hard to do, but I just lied. I'm gonna copy and paste this so we can see them both at the same time. You don't have to do what I'm doing. I just want to do it so we can talk about it at the same time. So you don't have to keep like flipping between the two pages. Okay, so the first one is sine and the second one is cosine. Do you see they have something in common? They both have those nice smooth curves. What else? There's a lot of things they have in common. Yep. What else? Besides Dylan, because you all have eyeballs. Nothing else? Okay. How could I get from cosine and change it into sine? Because they really look almost identical. How can we take cosine and change it into sine? Patrick. Like rotate it, right? Yeah. How far would you rotate it? What? How far would you rotate? I just did it. How far would you rotate? Oh, I can't go on top. It's not see-through. 90. I didn't hear what you said. Yeah, 90 degrees. If I rotate it 90. Now look at the x's. The x's don't look the same. But just the overall y values are exactly the same if I rotate my x's 90 degrees. If I shift my x's 90 degrees, the y values are identical. So when we input the angles and we get out the exact same y values in the same order, the graphs are going to look a lot alike. They're going to look a lot alike. Here, let me open up Desmos real fast. You can see how identical they are. And then we'll go and graph them. So I will graph sine x and cosine x. Let me just change my x-axis so I'm counting by radians. Do you see how they're nice, smooth curves, nice, smooth curves? And literally this point to this point is how far apart horizontally. 90 degrees, pi over 2. So if I were to take my red one and subtract pi over 2, they're now exactly the same. If she said subtract pi over 2, why did she type plus pi over 2? Because why? It's a horizontal translation, and those are always opposite. Exactly. So our transformations, by the way, are coming back full force. So those transformations that we did in chapter 1, if you didn't learn them, now's the time. We're gonna do transformations. But yes, they are off by 90 degrees or pi over 2. Okay, so go to the actual honors pre-calc notes now. We are going to talk about these words at the top, these vocab words in a moment. I just want to graph the parent functions first. So those are at the bottom because we were going to do that on the other page, but the other page was for my class that I know definitely never graphed these last year, but I wasn't sure about you guys. Okay, so we're going to first graph sine x. You'll notice there's only 5 points that I have in my table. I don't need every single value of sine around the entire circle. All I need to know is how high up it goes and how far down it goes. So like just going back to this Desmos, come on, let me undo this translation. I need to figure out how high up it goes and how low it goes. There's only 5 points that I need. And I will not have Desmos in front of me when I take a test or a quiz. So possibly having a way to figure it out without that is helpful. So what I suggest is if you do not know all your values of sine, the first thing you do is you go and you write the ordered pairs for the unit circle on the x and y axes. So 1, 0, 0, 1, negative 1, 0, 0, negative 1. So my x values are going to be the input. Those are going to be the thetas. Those are going to be the angles. That's what I'm putting in. So I'm going to go from 0 to 2 pi for my parent function key points. And then they're all going to be spaced the same. So I space all those the same. They just happen to be the x and y axes from 0 all the way to 2 pi. And then the y values for sine are the y values from the ordered pairs. So I'm just going to look at my y values from the ordered pairs. and I get 0, 1, 0, -1, 0. So that's going to give me the highest number, the lowest number, and the most middle number. And then we just have to make it look like a nice smooth curve in between. So on my graph, I'm going to graph 0, 0. Pi over 2 is 1. Pi is 0. 3 pi over 2 is -1. And 2 pi is 0. And then I just try my best to make it look like a nice, beautiful, relaxing curve. A little nice wave by the ocean. Yikes, that was bad. So you guys saw when I graphed it on Desmos what it kind of looked like. I just copied what it looked like. Now, this is an input-output kind of thing. There's nothing saying only input 0 to 2 pi. This graph can go on forever. I can input any x's I want. So now I'm going to copy the pattern. So if I go mountain, valley, what is it going to happen? What's going to happen to the right of 2 pi? There's going to be a mountain again. Oops. And then once it reaches the end of the graph, I'm just going to say, well, it's going to go down next, but I'm not going to finish. A little arrow will do that for me. Then I'm going to go the other direction. So think going backwards. I had a mountain in black, then a valley in red, then a mountain in red. What's going to come next? A valley, right? And it doesn't matter the color, but yeah. Just make sure that we don't have 2 mountains together and we don't have 2 valleys together. It always goes mountain, valley, mountain, valley. Okay, and then we've got our nice smooth curve. So the reason why I colored the original part in a different color is that is one full cycle, one time around the circle for the sine graph. And we want to be able to recognize what one cycle of sine looks like. We'll come back to that in a second. Let's do the cosine. So cosine, the input is still going to be the thetas. So 0 to 2 pi and evenly spaced in between. And then the output is going to be the cosine of those thetas. So the output is actually the x's from the ordered pair, which could be confusing. So the x's for this equation are the angles. The output are the x's from the circle. So at 0 degrees, cosine is 1. Pi over 2, 0. Pi is -1, then 0, then 1. And it's going to look a lot like sine, where we're going to have that curve with the highest number being 1 and the lowest number being -1 and in between being zeros. We're just like starting at different x's. So at 0 is 1. Pi over 2, 0. Pi is -1. And then I'm going to color in the one cycle with a different color so you can see it. And then once I color that in, I'm just going to continue the pattern with the mountains and the valleys until I get off the graph and then draw my like arrow in the direction that I'm going off the graph. So when you get to this part, you want to be able to look at sine and look at cosine, the one cycle, they look different. Once you start graphing it all, it pretty much looks the same. But the one cycle looks different. One cycle of sine is like a mountain into a valley. But for cosine, it's like you're at the top of two mountains going to the valley in between. Okay, the one cycle looks different between the two. So you should be able to recognize that. Now we're going to talk about the words above. So there's vocabulary, and the first one is called the period. And the period has to do with the cycle. Just like another period that you know in life that happens on a cycle. Like there's a reason why it's called that. The period in this is horizontally how far before it starts to repeat again? 2 pi. The parent function period is 2 pi. This is the parent function period. What kind of transformation would take that period and like make it less long or more long? A horizontal stretch or shrink will change the period. And I believe it says that in the vocab above. What's the next one? Amplitude? Is it amplitude? Yeah, so the next one is amplitude. Looking at the picture, the amplitude is how far above and how far below this graph goes from its center. So you can see the center, which we should probably go over that too. But you can see where the center is, especially with this one. You can see where the center is. How many units above and how many units below is its amplitude? Do you guys know what the answer is? No, what is the answer for this amplitude, this particular one? 1, yeah. Now, what would change that would be if we had a vertical stretch or a shrink. That could make it taller or less tall. It would be like stretching it vertically. Oh yeah, when I talk about how far above and how far below the center, that center has a name also. It is called, it's the next one down. It's called the sinusoidal axis. I was just trying to pick a color. So in green, that's my sinusoidal axis. Sinusoidal. And it's just the equation of that midline. So for the parent function, what line did I just draw in green? Y equals 0. What could change where that line is? What kind of transformation? A vertical what? Translation. We translate up or down, that will change the midline. And then there aren't any for this one, but up in the definitions, excuse me, there is a vertical shift, which is a vertical translation, which I just talked about. That would change our sinusoidal axis. And then there's something called a phase shift, which is just a horizontal translation, left or right. But they call it a phase shift, specifically in this in trigonometry. And then right here, I just have the transformation formula for sine and cosine. It's the same as the generic one. Just remember that this b has to be factored out. It's the same that it was when we were doing transformations in chapter 1. That b value has to be factored out. What does the a value in front refer to? It could be a vertical stretch or shrink. That's something else it can be also. Vertical stretch or shrink, something else it could be. No, that is going to change the amplitude. Something else the A could be. Allison? Reflection in which axis do you know? Vertical or horizontal reflection? Vertical. So that's going to be reflect in the x-axis. So that could be a reflection. If there's a negative there, it'd be a reflection. If there's a number other than 1, it would be a stretch or a shrink. Remember, the negative and then the number itself are 2 different transformations. Okay, the b value that has to be factored out, what could that be? Horizontal stretch or shrink. Or reflect in the y-axis. The c value is a horizontal translation, which in this chapter they call it a phase shift. And then the D would be a vertical translation, which they're going to call a vertical shift. Oopsies. When you're ready to go on, I'm going to leave this up for a second for anybody still copying. When you're ready to go on, I'm going to the next page. We're not going to get to any straight up graphing today. We'll save the graphing till tomorrow, but we just want to be able to recognize some of these features in graphs that are already graphed. So we're going to find the period and the amplitude. We can do that using what we know about transformations, or we can look at the graph. So I'm going to first look at the graph. Then I'll explain it using the equation. So for finding the period and the amplitude, looking at this equation, it is a sine. So I'm going to try to seek out that sine curve. The sine curve looks like a mountain to a valley. So I'm going to look where in the center, it starts as a mountain, goes to a valley, and then ends right back in the center again. There is a place where I see a sine curve. So the period is the horizontal distance length from start to finish. So think on the x-axis from start to finish, how far did I travel? Just horizontally. Emma. Pi. That is correct. Then the amplitude from our sinusoidal axis, which is the middle, we say how far up and how far down does it stretch? 3. So that's our period and our amplitude. You can also get those from the equation. Here's the 3. It's the vertical stretch in front. Okay? The period is a little bit different. We have to know that the parent function period, parent function period is 2 pi. Parent function period is 2 pi. And then this 2 right here is a horizontal shrink by a factor of 1/2. So when I say by a factor of 1/2, that means multiply. So that's telling me to take the original parent function period and multiply it by the horizontal shrink. And when I multiply 2 pi times 1/2, what do I get? Pi. And that was my period that I also got by looking at the picture. So you could get it either way. You just have to apply the horizontal stretch or shrink to the parent function, period, to get it. So the next one is a cosine graph. So we're going to look and try to find that cosine picture, which starts at the top and ends at the top of two mountains. There's a valley in between. This is not the only place on the graph that I could highlight that same picture. You could do it in many different places. You just have to find one of them, though. So we need to figure out horizontally the length. We define the period, that's the horizontal length from the start to the end of this one cycle. Is this one a little bit harder to figure out because you're looking at the graph? Is it because you're looking at the graph? The graph's not labeled very well. It doesn't give you a lot of information. You could maybe figure it out, but it doesn't give you a ton of information. Corey? It is, and did you get that from the graph? No, you did not. You took the parent function, period, which is 2 pi, and then you multiplied it by the horizontal stretch or shrink. So we look at the horizontal, that's a 3. So what do I multiply by? 1/3, right. So my period is 2 pi over 3. Which, gosh, that just took way less time than trying to look at my graph and figure it out. How about the amplitude? Now, did you get that from the graph, or did you look at the equation? The equation was easier, but if we needed to find it in the graph, we could find it in the graph also. Okay, the next one is a sine graph. So look for the sine shape. Here's one. It's not the only place it is, but there's a place. Now, you don't have to use the graph. I need to know the period. Charlie, you got the period?
Yeah.
What?
6 pi.
6 pi is correct. Did you use the graph or did you use the this? The equation. So you did 2 pi and then you multiplied by 3 over 1, which is the reciprocal of 1/3. And then the amplitude, Emily. 3. Did you almost say -3? Yeah, but why did you stop? Well, the negative is a reflection. The 3 is the amplitude, right? Okay, and then the next two, they don't even have pictures. So you literally have to use the equation. I'm going to go ahead and write those down while you guys try them on your own. So we should get the first period 1, amplitude 1/4. Second one, period is 20, amplitude is 2/3. Questions? So in my other class, we did these 4. Just going to look at them just overall. It's just basically what is happening from F to G, and G is the darker one in each of these. So if you're looking from F to G, what kind of transformation took place from F to G in the first one? What kind of transformation went from F to G? There's only one. A vertical stretch, right. You could probably even figure out the vertical stretch by a factor of 2, but we don't need to. What is happening on the second one from F to G? G is the darker one. What's happening? What do you think, Lee? Is a horizontal shrink. It's like we're taking that sine graph that's kind of like a spring, and just squishing it together and making that spring thing like closer together. Horizontal shrink. And we could figure out what the factor is, but I don't really have enough time. What is happening in this one from F to G? A horizontal translation. Yep. Yep. And that was what I was going to do next. They're going to call it a phase shift. So when you have to answer, what's the phase shift? That's just like went to the right pi.
If on the test, you have to like write like horizontal translation. Is it better?
No, it'll be like phase shift and you'll type right pi.
Does it matter like whatever term we use? Like if we were tested on it, or can we use?
Is there a different term other than right?
No,
You won't type in phase shift.
Okay.
That'll be like what you fill out.
Okay.
Yeah, you won't type in phase shift. Okay, and then the last one, what's happening from F to G? A vertical translation or vertical shift, yeah. So we did not get to the graphs, and I want to make sure that everybody knows how to do these with tables. So you can work ahead. I wouldn't encourage you, if you didn't do so great with transformations in chapter 1, to work ahead. But you can definitely go and answer, what's the period of this one? What's the amplitude? You can answer some of those questions if you don't want to have more to do tomorrow night. If you want to get a little bit ahead, you can answer some of that information for sure. But then tomorrow we're going to do the graphs. So we'll have like three examples tomorrow. And then on Thursday, we're going to do example 6. So this is a 3-day process for us.